morning everyone. Today my topic is losses in a DC machine and efficiency of DC motor. Losses in a DC machine. You can observe the losses are classified into mainly two types, that is constant losses and as a variable losses. So the constant losses which remains constant at all loads are the type of losses I am calling as a constant losses. The constant losses are mainly three types, that is iron losses, mechanical losses and shunt field losses in case of the DC machine. And the variable losses, the losses which vary with load, the type of losses I am calling as a variable losses. The variable losses mainly in case of the DC machine, that is copper losses in armature winding and copper losses in series field winding. Okay. And before discussing of this thing, what are the power stages in case of the generator and motor? So you can observe the power stages in generator. First, mechanical power is input, and that mechanical power is converted into electrical power, and the output is electrical power output. So we are giving the input is mechanical power. In the process, we are getting the conversion process mechanical to electrical, so that is generated EMF and armature current, and at that place the output power is equal to terminal voltage into load current, and in between the input power and the conversion process in case of the generator we are getting mechanical losses, that is friction, windage, stray losses and core losses. In case of the conversion process to the output process, we are getting the losses in case of the generator, that is electrical losses. Coming to motor, the power stages, the input of the motor is electrical, it's the electrical power input we are giving, and the conversion process, that is electrical power converted into mechanical power, and mechanical power output we are getting here. Here three stages are there, here also three stages are there. So then the in case of the motor, in between the input to the conversion process we are getting the electrical losses, and in between the conversion process to the output process we are getting the mechanical losses, that is friction, windage and stray losses. So these losses are there in case of the power stages, in case of the DC machine. So power stages in DC generator, that is mechanical power output, already we discussed, that is mechanical losses we are getting in between the input to the power developed in the armature winding, we are getting the mechanical losses and stray load losses and iron losses, and in between the mechanical power developed in the armature to the output power we are getting the electrical losses, that is armature copper losses and shunt copper losses and series copper losses we are getting. These all are the constant losses, these all are the variable losses. And in case of the motor, similarly the input is the electrical and the mechanical power developed in the armature, and the third stage is output power, that is mechanical power. So that's why the input losses here mainly is the electrical losses, that is armature copper losses, shunt copper losses and series copper losses we are getting, and in between the mechanical power developed in the armature to the output power mainly we are getting the constant losses, that is stray load losses and the mechanical losses and iron losses. Losses. So copper losses is armature copper losses and shunt copper losses and series field winding copper losses. Mechanical losses is friction at brushes and bearings places we are getting the friction losses. At between the stator and rotor, means between the armature winding and the field winding we are getting the windage losses, And the magnetic losses are hysteresis losses and eddy current losses. And the stray load losses are stray iron losses and stray copper losses. And the hysteresis losses. The hysteresis losses is equal to the formula according to the magnetic curve. We are getting the hysteresis coefficient into maximum flux density power 1.6 into frequency into V. Here the stem hysteresis coefficient depending on the material, and the maximum flux density, the units are Weber per meter square, and N here again F is the frequency of magnetic reversal per second, and V is the volume of magnetic material. So this formula is depends on the magnetic curve. And also next losses is eddy current losses. In the eddy current losses is depends on the frequency and again volume and also speed. So this eddy current losses is equal to Ke into B square M into F square into V square into T square, where Ke is the eddy current constant, maximum flux density whole square, and F is the frequency of magnetic material, and the T is the thickness of magnetic material, V is the volume of magnetic material. So that is W is directly proportional to the frequency square versus V square. And the voltage condition for maximum output power in case of the DC motor. In a DC motor, the armature will develop the mechanical power and as well as the mechanical power we are expressed in terms of the mathematically of the approximate mechanical power is Pm is equal to V into Ia minus Ia square into Ra. So here V and Ra are this V and Ra are fixed. Power developed by the motor depends on the armature current only. So for maximum power, that is the mechanical power is derived with respect to the armature current only, because here V and Ra both are constant, is only the armature current is varying. That's why for getting the voltage condition for maximum output power, we are doing the derivation with respect to the armature current for the mechanical power, that is dPm by dIa should be is equal to 0. That is dPm by dIa is equal to V minus, if you are deriving with respect to the Ia, you are getting the V, Ia square is 2 into Ia into Ra is equal to 0. So then Ia into Ra is equal to V by 2 already. Now V is equal to Eb plus Ia Ra for DC motor. That is where I am substituting here Ia Ra is equal to V by 2. That is Eb is equal to V by 2 I am getting. That is the back EMF will be is equal to half of the terminal voltage. Means mechanical power developed by the motor is maximum when back EMF is equal to the half of the applied voltage or terminal voltage. That is armature current at maximum power will be is equal to V by 2 Ra we are getting. So that's why the P maximum power will be is equal to, according to this equation, we are getting V square by 4 Ra, and efficiency at maximum power will be is equal to 50%, because we are getting here mechanical power developed by the motor is maximum when the back EMF is equal to the half of the applied voltage. That's why at this condition the maximum power efficiency is equal to 50% only. Okay. Now efficiency of DC motor. So let us consider V is the supply voltage to the DC motor, and the motor will be draws current I from its supply mains during its operation, so that the input power to the motor is electrical power, that is the V into I. V is the supply voltage, I is the terminal current. And after the second stage, that is after copper losses from the input to the according to the power stages in case of the DC motor, the input to the conversion process, we are getting the losses. That's why that is after copper losses, the armature develops the mechanical power in the armature winding, that is PM is equal to EB into IA, where EB is the back EMF of DC motor, IA is the armature current of the DC motor. So after that, in between the conversion process to the output process, according to the DC motor power stages, we are getting the friction losses. So in between the conversion process and as well as the what? Output power. So that is the after friction and windage losses, the mechanical power appearing at the shaft of the motor, not output. What I am saying here, shaft of the motor for doing the work is, that is P output power is equal to P mechanical power minus the WC, where WC is the constant losses, where the WC is the constant iron losses in the machine. So that the approximate power equation of the DC motor is the output power at the total end will be is equal to VI minus IA square into RA minus WC, we are getting here. So that, but there are other two losses that we have not considered here for the simplicity of the power equation. That is, these are the copper losses is the shunt and series field R. We are not considering. So the power equation, output power equation is equal to VI minus IA square RA minus WC we are getting. So then let efficiency of the DC motor is now what? The efficiency of the DC motor is P output power by P input power. What is output power here I am getting here? VI minus IA square into RA minus WC divided by input power is VI. So this is the efficiency of DC motor. So for this efficiency of the DC motor, we are finding, for this efficiency of the DC motor, we are finding the condition of the DC efficiency, maximum efficiency of the DC motor also. So that is here, that is condition for maximum efficiency here, that is let the generator output, this is the condition for maximum efficiency for DC machine, means this is the condition is for the DC generator also and as well as the DC motor also. So that's why I am taking either DC generator EMF efficiency equation, or otherwise you can take from the motor efficiency equation also. Whatever you can take, you will get the efficiency condition will be same only. So that let us we will take the generator. Let us the generator output is equal to VI, that is electrical power, and the generator input is equal to mechanical power. So mechanical power we can't calculate directly. That is the generator input power is equal to, we are calculating, that is output power plus losses here. That is VI, output power is equal to VI. The losses are armature copper losses plus constant losses. That is VI plus IA square into RA plus WC. Here what I am doing here, I am assuming the armature current is equal to terminal current, because shunt current is very small compared to the armature current. So that's why what I am getting, according to the generator equation, IA is equal to IL plus ISH, or IL is equal to IA. I am taking this ISH will be negligible, then you are getting the IA is equal to only I. That is only I am taking here the let VI plus I square RA plus WC I am taking. Okay, so then the efficiency is equal to power output by power input. That is, what is the power output here? V into I. What is the power input here? VI plus I square IA square RA plus WC. Or otherwise you can take VI by VI plus I square RA plus WC. So if you are taking the common in case of the denominator is I and the numerator is I. So if you are taking here I is the common, this denominator numerator I will be cancelled, then I am getting the 1 by 1 plus I into RA by V plus WC by VI I am getting. But for finding the condition for maximum efficiency here, to obtain this one, the denominator should be the minimum. Denominator should be what? Minimum. So therefore, differentiating the denominator with respect to the armature current or this total current, and equal to be 0, because here this constant losses will be constant and the voltage will be constant and the armature resistance also constant. Only the current is varying. That's why we are taking here differentiating the denominator with respect to the I, and that will be is equal to 0. That is d by di into 1 plus I into Ra by V plus Wc by Vi is equal to 0. So if you are derivating here, I am putting the 0 plus Ra by V plus Wc by Vi square is equal to 0. If you are simplifying this equation here like this, Ra by V plus Wc by Vi square. So then if you are saying 1 by V is the common, if you are taking, then what I am getting now? 1 by R plus Wc by I square I am getting is equal to 0. Then if you are taking this with 0, then what I am getting? 1 by R plus Wc by I square is equal to 0. So then what we will get now here? Wc by I square is equal to 1 by R. Means this is not 1 by R. I think so. This is Ra by V. Ra. Sorry. This is, I am getting here Ra by 1 means you are getting here. Sorry. So you are getting here, for getting Ra by V plus Wc by Vi square is equal to 0. Then what I am getting here? Ra plus Wc by I square is equal to 0. That is Ra plus Wc by I square is equal to Ra. Then what I am getting here? Wc is equal to I square into Ra. I am getting here. I square Ra is equal to Wc we are getting here. Therefore, the efficiency is maximum when the I square Ra is nothing but as a copper losses or nothing but as a variable losses. Wc is the constant losses. Means the condition for maximum efficiency of the DC machine is the variable losses is equal to constant losses. Then this is the condition. At this condition, we are getting the maximum efficiency of the DC machine, either in case of the DC generator, either in case of the DC motor also. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.